Hi, today I would like to show you a general steel cross-section in SCIA Engineer. We will start with a little bit theory about the classification of the cross-section. We will go through the input of the cross-section from DWG file, some parametrization, then some tips and tricks about auto design and evaluation of stresses, and at the end I would like to show you some mistakes I have seen on the hotline, so things you should prevent. My name is Ivan Beleš and I'm support engineer for SCIA and Idea Statica. We will start with a little bit theory. Usually in SCIA Engineer for steel members, 1D objects or 1D elements are used. This is a line with some characteristics. And we have, I will show you some table. We have the calculation of internal forces. Let's say something like this bending moment. So we have bending moment, shear force, axial force. And then we have the steel checks according to Eurocode, calculation of stresses and stability calculation and whatever. Eurocode knows 1, 2, 3, 1, 2, let's say 2.5 and 2.5, 1, 2, 3, 4 classes of cross section. We have the class 1, class 2, class 3 and class 4. If we have a robust cross section with enough rotational capacity, then this cross section can be checked with the plastic properties and also analyzed with the plastic hinges. So in this case, we have plastic analysis of internal forces and we have plastic checks. If the section is less robust, so that we cannot achieve enough rotational capacity for the plastic hinges, then we need to calculate internal forces with the elastic properties of the cross-section, but we can check the cross-section with plastic properties. This is the class 2. Class 3 is again a little bit less rotational capacity, so we can analyze the cross-section with elastic properties and check also with elastic properties. So we have elastic and elastic. And then we have class 4. These are cross-sections. They have stability issues at some parts. For example, we have very thin web, and this thin web can get buckling from the load. So then we run also elastic calculation, elastic checks, but with effective properties of the cross-section. Only the remaining part which is not buckling. So this is the classification in Eurocode 1993-11. So, and for us it's important, if we create a general cross-section in SCIA Engineer, to create it correctly, that SCIA Engineer can classify this cross-section automatically. Cross-section has a standard shape, so let's draw it. I draw it maybe not very elegant. Let's say this one. And we have also some roundings or welds. This shape is used for the calculation of cross-section characteristics. Cross-section area, torsional constant, and so on. But for the classification, this is not very useful, because Eurocode says that the cross-section has some parts. So we have to split the cross-section into some parts. Let's say this one and the other side I will not. Okay, I draw it completely. Not so nice. So we have so we split the cross section into smaller parts. These parts are defined by width and thickness, and then we can look at each part at this ratio between the width and the thickness. And for this ratio, there is a table 5.2 in Eurocode 1993-11. And in this table, there are limits. So if we have some ratio, let's say 20 or less than 20, we can classify this cross-section as class 1. Or this cross-section part, not the full cross-section. If it's more, then it's class 3. And if it's more than, let's say, 80, it's class 4. So there are limits for the classification. Each part gets one class, and the highest class of the cross-section decides about the class of the full cross-section. So let's say only one teeny part, let's say the web is class 4, then the full cross-section is calculated as class 4. These cross-section parts are, so there are 4 types. 4 types. Okay. So there are parts, they are supported from 2 sides. And this is part which is called I. This is internal part. Then there are parts, they are supported only on one side. And depending on the, or let's say this one, depending on the symmetry, it's a symmetrical outstand, or if we have, for example, a U section, then this is unsymmetrical outstand. And then we have this part which is not calculated. This is F, like free. So this is the basic. There are in Eurocode for aluminium is a better explanation. Also, some additional parts, reinforcements are explained there. But this is the basic which we will use now in SCIA Engineer. And then there is also one quite important part. If we have, let's say, H section, I draw it on this way. Then we have welds or roundings. These parts in Eurocode are defined with this clear width. This is the C. It's from the weld to the end of the cross section. And for example, for the web, it's this length. This is the C. And so this is in Eurocode 1993-11 and 1993-15, so defined. But in Eurocode 1993-13 for cold form sections, this distance is for the bruto distance from axis to axis, because there are no welds, so there are only roundings, and these roundings have to be calculated in the width. So I think this is everything for this theory, and now we can jump into SCIA Engineer. Now we can open the cross-section editor. It's in libraries, and we can create a new cross-section. It's this general cross-section. This is the general cross-section editor. Watch your units. You don't see the units here in this dialog, so therefore you have to define it before you jump into the editor. So we can draw directly polygon, thin wall, but I will import it because I have a little bit complicated cross-section. So I go to the import from DWG or the XF, whatever you want. And there are more ways, or let's say 2 useful ways how you can create this cross-section. If it can be simplified. Then you can directly draw the thin wall cross-section with a little bit limitation, because we will not consider the size of the welds in this input. But sometimes it's not necessary. If the size of the welds don't jumps, if the distance is not so, or difference between the distances is not so high that it jumps, for example, from class 3 to class 4, then you can use also this bruto width of the cross-section part, and you can import it like I will show it at the moment. So I will disable all layers and I will use only this shape and change to thin wall. Select all of the parts. You can control the size. Here is the rectangle which describes the full cross section, and if the units are not correct, you see it here. And then we go to import selected. Let's define the thickness to 8 millimeters. This is for the webs and for the reinforcement. Okay, it will be inputted to 0, enter in the center. Now I can change the thickness to 20 millimeters. So what is SCIA Engineer doing here? Because we draw exactly to the boundary, SCIA Engineer will automatically extend this part until to this point. And I hope it will also split these parts to more points. So what we cannot consider in this input is the correct width, but we will have this bruto width of the cross-section part. We are on the safe side. So because the C to T ratio is a little bit bigger, then we sooner jumps to higher class, and this is on the safety side. So this is done. I can close it, update the cross-section, and look at the initial shape. Oh, that's correct. So you see this line was split automatically. So we need to define these parts. SCIA Engineer automatically looks if this part is supported on one side or on both sides, and writes unsymmetrical outstand or internal part. I don't know if it decides also symmetrical outstand, but I never have such simple cross sections. So this is unsymmetrical outstand. So this is everything correct. What we have to change is we don't need to classify these small parts. So we change them to F. So F is not classified. So we can change all these smaller parts into F. And this one. And the last one. You see the picture jumps to the full size picture each time I change something. So if it's annoying for you, then simply go through these lines. You see all these parts, they are red, and you can change the type of this element. And if this is everything done, then we can update the cross section and look at the classification. We will input some random internal force, let's say pressure, update, and we see all these parts. We see that 3 is class 3. 15 is also class 3, and all other parts are class 1. It's automatically classified. If you have class 4 cross section, then you can look for compression, bending, if it's some critical, and maybe it will get also class 4. So, but this will be done automatically during the checks for each load case combination, separately for the cross-section check and for the stability check. SCIA Engineer is analyzing the cross-section and calculates the correct class. This is important. For standard cross-sections, from the library, let's say this HAE200, we can update it. Then we see this initial shape. It's predefined, and you see 6 is defined as F. If you have welded section, let's go to this welded. No. Where is it? Sheet welded, for example, this one. I hope it's defined. Yes, you see this A. Let's say 10 millimeters. This is the size of the weld. And if I am correct, then you see here we have defined a weld, and we get, this should be the weld. This distance is recognizing the weld, and the 6 is then as F. So, and this C to T ratio for 5 is a little bit smaller than from axis to axis. But we have inputted our cross-section without these welds or rounding. This is the simplified way how you can work. Sometimes it's okay. You are on the safe side. Another way how we can import the cross-section is if we have a little bit complicated cross-section, or we want to consider these welds, then you can split the input and use polyline or polygon for the calculation of the cross-sectional characteristics, like cross-section area, shear area, and so on, and another simplified shape for the classification of the cross-section. Then we can split it. So we go to this, let's say, more complicated input, use the same file, and what I have there, outline, and I have also thin walled representation. First we will import the outline. You can directly draw in your CAD program closed polyline. So you can create a polyline and close this polyline. You can, if you want, you can do it in one piece. You can import the outline and you can import the opening. This is correct way. But later I would like to show you how you can evaluate stresses for each part separately, and for this input it's better if we split the cross-section to smaller parts. Let's say each plate is one part. This is outline split, and here you see I have already closed polyline, so I can directly click on them. But this one is not defined on this way. These are simpler lines. If you have such DWG file, maybe download it from internet or so on for some aluminium section, then you can close these polylines also in this editor. Go to select lines, then you select all these not connected lines, say connect curves, check if everything is okay, is one polyline from 4 parts and there is nothing left. And it's necessary to close it, and then we have some polylines, so I can select them separately or by window and import. I don't need thickness because this is polyline 0, enter. The cross-section is defined. You can close it. I have FEM analysis, so I can analyze the cross-section. Use it also in the calculation, but because we don't have these parts for the classification, SCIA Engineer will use this cross-section as class 3 each time. Not class 4, no class 1 or 2. It's not an issue that it's not class 1 or 2. You are on the safe side, but if it should be class 4, then we are not on the safe side. We have to extend this input a little bit, so we can go to edit again, and I can add this so-called thin walled representation. Not the thin walled, but the thin walled representation. But, so I could draw it, but I'm a lazy man, so I don't want to draw it. I have prepared it in DWG file. and this is one layer. But I cannot import thin walled representation. You see, this is thin walled representation, and we have only thin walled. I will import it as thin walled. I know it's not correct, but I will do it. Select everything, import selected. Let's say, I don't know, 5 millimeters is the thickness. Okay, so I don't want to overlap them because then I have too much lines one over another. So I go to 1000 millimeter on the right side. This is the thin walled section, which we will not use, but we can draw on this background the thin walled representation. If you start thin walled representation, let's say 8 millimeters, SCIA Engineer jumps here to thin walled representation, so you don't see this thin walled, so you have to break it one time, change to thin walled and boundary, and start again. We have to restart one time. Okay, and then we can draw this cross section, this thin walled representation correctly, and this is the weld. This will be the part with the weld here. I go from here to here. If this is rounding or weld, then I have here and here and here lines. We will draw line. I draw also these lines exactly. I think it's not necessary because this is the part F. It's not classified. It has no influence. I checked it, but I'm really not sure what happened in the next version. So therefore, better if you invest time, then do it correctly. From point to point and another point. You don't need to draw extra lines. You can simply use a polyline, but you need to split them on these dividing points. Here? Yes, here. Okay, it's correct. And to the top. Here and here. Okay. And we need one more part here. Okay. Now I can select these parts and mirror them on the another side. So what we need is cursor snap setting midpoint. F8. Does it work? No. Relative. Dot grid only, orthogonal. Okay, then go to here. Not remove. Okay, and then select this thin walled representation and we'll copy it from the top point to bottom. Okay. They are defined. Now I can select them. I'm again lazy to select all these imported parts and not this one and this one. So you have to select correctly the thicknesses to make it simpler. And then I will move it from here, 1000 to, back. Move it from 0 to 1000. Okay. And then I can delete all these not necessary parts. This is defined. For this, this is not correct. I see it's not vertical. So I hope it will be vertical. So this is 340. No, 1805. And what is this point? 1805. Okay, looks great. Okay. This is the thin walled representation. We have to change the thickness to 20 millimeters, and then I can select it and move it back from 2000 to 0. And now they are one over the another, close it, and let's check if it's okay. Update, initial shape, and you see this is correct. This should be our weld here. We have this part correctly defined, and from weld the web again. And this is unsymmetrical outstand, this is correct, this is automatically also calculated as internal part. Oh, sorry. What we have to do is to change the type of these F parts. In the past, I simply selected it and changed to F, but then it jumps back. So go simply through the lines, and if you see this is a small part, 3, 4 is correct, 5 is F, 6 is also F, 7 is F, 8, 7, that was 7, is correct, 8, 9, 10 is also F, 11 is F, 12, 13, F. It's a little bit boring part of the video, but you can jump through it. I want to do it correctly. And define correct all these parts to F. It would make not so much difference, I think, if I leave it as F. But it's better we do it correctly. Then we are almost at the end. This is correct. This is also F. And 26 is F. 27 is I. 28 is F. And 29 is also F. And 30 is correct. Done. Update. Check the classification. For example, again, -100. Update is class 3 cross-section. And we can also look at the effective cross-section and check if it is, you see, if it is class 3 or class 4 section. But this will be automatically done during the checks, so you don't need to run it, it's only to check this part. We can look at the checks. I will close it. Change, let's say this one member will be changed to the last one. This was the inputted parameter 1. I can recalculate it and run the checks. Okay, and still checks. So let's say this one, this was our last. What we need is detailed output with tables, and you don't not need tables and formulas, but the detailed output is good to check the results. And we see now the classification of the cross-section is class 3 classified. That's okay. If we would use it only this cross-section without this thin-walled representation, we would get a remark that this was classified as class 3, and you have to adapt it. So maybe you are on the safety side because you cannot calculate plastic, but if it's really thin-walled and should be class 4, then this is not on the safety side. Small explanation to the input. It can happen that you have some, let's say, aluminium section. Let's say something like this. So and so. It goes down. And so this is only a part of cross-section. In the 1999 Eurocode for aluminium, there is also an explanation how you have to simplify the cross sections. And if not in Eurocode, then there is this design book for aluminium structures. Then there are also some explanations with pictures. And in this way, we will draw such line. So we will simplify it. Not draw everything, but we will draw only a line with one thickness, and this will be classified as part, and this also one, but not all these details there will be not used in the classification. So you have to simplify it, and therefore it's also very good to split the input of the polyline and input of this thin wall representation. Now we are finished with the important parts of the input, but we can go through some additional explanations. Ctrl J is for cross-section library, and I have already one prepared where I have also parameters. I can edit this cross-section, edit. Each part of the cross-section has some points, and you can create parameters. There are parameters. Some of these parameters are parameters you want to input, where you want to decide about the width, the cross-section height, the thickness, roundings, and so on. You can start with these parameters, and they are inputted as a value, and you have to activate this checkbox, and then they will appear in the cross-section properties in the cross-section library, and you can change it. So you don't need to jump into the editor and change everything again. This is for the case you have some standard, your own company cross-sections, not if you want to have it only one time in one project. But if it repeats, then it's worth to invest a little bit time and create all these parameters. So you can create parameters for the input. You can also use some range where you can define minimum, maximum. These ranges can be also calculated by formula. And then we have parameters for the coordinates. I do it on that way that we have horizontal y and vertical z axis. So I create for each vertical or horizontal point or coordinate one value or one variable, so that I don't need to think about all these variables, and I start left, go to the right from bottom to top, and all points are then defined, so I don't need to create them again. What is important, it's case sensitive, so it's not equal if you write b with upper or lowercase, and the parameters are calculated in this sequence. You cannot use, for example, for parameter 7 something which is inputted in parameter 2 or 3 rows below. All parameters you want to input or use in 7 has to be already defined. You see, this is b2, b divided by 2, b is already defined. You can also use another parameter calculated as a variable in the formula. For example, if I go to the middle, then I go to the right side from minus to plus, so simply multiply with -1. So it's nothing complicated. You can define all parameters, they are checked, and then if you have done it, select all points in the same row, for example, and you see this is y1. Usually I use also underscore, but it is sometimes confusing. So then I select all these parameters and change it to y2 and so on. So then you can draw dimension lines. Let's delete them. And there are also dimension lines, horizontal, vertical, whatever you want. Simply select one point, select another point, place it. And you can also, it's not bad if you write a label. Let's say b is equal, what do I have? Okay, b is equal blank, and it's done. So, and then you know what you have to input. H is equal this, and this is, for example, a, if you want, and it should be placed on the left side, so you can make really nice drawing. Then we know what is H, what is B in the drawing, and it's easier if you give it to your colleagues or to your partner on some company. Tips and tricks. So we are at the next topic. I will recalculate the structure. It's necessary? I don't know. I will recalculate it. And let's use the cross-section. We can use the last inputted cross-section, Ctrl J, edit. And there are named items. And because I have inputted this part as a separate polyline, I can say this is one part with one name. Let's say top flange. So I can select it, go to this 3 point and say this is top flange. Top flange. Okay. And, oh, sorry. It's there. No, again. It's top flange. Okay. It's correctly defined. And let's say I would like to evaluate the stresses also in this point 15. And this point should get the name, let's say, reinforcement left side top point. It's a fiber. Okay, so it gets also a name. We have one part and one point with a name. And I need to recalculate again. And if we go to the results, here are the results. We have stresses. Let's say for current selection. These are stresses for the full cross-section. But I would like to know how is the distribution or what is the maximum stress only on the top flange. And then you can go to, where is it? Fibres. No, cross-section parts, named cross-section, top flange. This was defined, and calculate. And this is the stress, the maximum stress from the top flange. And if you want, then you can go to fibres, named fiber, and we have this one fiber in this point. And then I can evaluate the stresses only in this one point. It's almost zero because it's in the middle only with the thickness distance from the center of the point. This is the evaluation of the forces, the stresses, and we have also auto design in the checks. We can go to the steel checks, and if we select the filter to cross section and select this cross section, it was not the last one, this is this one, I hope. And if you want to run the auto design each time, select the type of selection to all, because SCIA Engineer is selecting the automatically all members with this one cross section. And then we can go to auto design. In auto design, you can select one dimension, or you go to advanced auto design, and if you have these parameters, you can select each parameter for auto design. So it's activated. We have step of 10 millimeters. We start at 300 millimeters and go to, let's say, 600 millimeters. We want to change the height also in steps of 10 millimeter, also from 300, let's say, to 700, and maybe the flange, each 2 millimeters from 12 to 30 millimeters. And then simply search for optimal, and SCIA Engineer will go through more cross-section and calculate the optimal cross-section according to all the checks. And now we got the correct cross-section for 80 to 700 and the unity check is 1. I go back with cancel, so I will not use it. It can happen that you have some cross-sections on stock, so you cannot freely combine some width with some another height. So you have, let's say, 5 cross-sections with predefined height and width and thickness. In such case, you can go to Structure and Analysis and go to the cross-section list. And then you can create a new list. I have predefined it already, but it's like new created. And for each dimension of the cross-section, which is in the parameters, you need to create a list. All lists for this cross-section need to have the same amount of parameters. So if you say I want to have 3 cross-sections, then for B, for H, for E, you need 3 or 5 elements. So I have decided 3, 5, 6, 700. Also for the height I have 3, for the reinforcement width, for the flange thickness, web thickness, and for the weld size. Each time the same amount of parameters. If you have it, then you can go to the auto design and you can change it to coupled set of auto design, and then you have all these lists and you can select this list. This is the B which I have prepared. These are the parameters and here are the lists which we have prepared. B, H, A, F, and S, and W, and then you can run this optimization. Oh, it's done. Okay, it's the minimum cross-section which I have defined. So there is nothing to optimize. But this is the way how you can do it. What can you do wrong in the input? Let's go to the cross-section. Create a new one. And I will import it. And there is 10 volt. This one. And I will import this as a 10 volt. Looks great. Import selected. Let's say 8 millimeters will be imported at 0. Enter. Then I change the thickness to 20 millimeters. Okay. And you get this message. Some 10 volt sections overlap. This is because of this part, because we have drawn the line not to the boundary but to the center, and then we have this overlapping part, and this overlapping part blocks you from the calculation with the FEM analysis with this full FEM. This will not work. You can only change to Krasov-Zhuravsky. But then also I have seen in some situations the torsional constant, for example, is then wrong. So this is not the correct way how you should import cross-section. So let's deactivate it. If you use this 10 volt cross-sections, then draw it. This is the center line with the thickness, and draw another center line directly to the boundary, not to the center. Then it's correct. SCIA Engineer adds automatically here a small part of the cross-section, connects it, and splits also this one line to 2 lines. You can check it, but it's done automatically. It's also described in the online help. What you also should not do is don't create a gap. Also a small tiny gap causes that it's not, then we don't get this part, so it's not connected. Then we have one line here, one line is here, and they are not connected. And the third one, if you draw the thin wall representation, then you have, let's say this was our cross section. This was the middle part, and then the bottom. So, and this is the symmetrical axis. Then you should split it. So you at least split in this point and this point, or better here also at the welt. So this is one line, this is one line, this is one line, and this one. So then SCIA Engineer automatically knows this is the C. Don't draw one line here and connect it here. If you create 1D elements and you create one line and second line, then it's automatically connected in SCIA Engineer with this double red line. But this is not the case in the cross-section design. You have to split the lines. You can draw one line and another line, or you can draw one polyline, but you have to create this one point where it should be connected. So, and if you create this thin wall representation, then you have to go to the center. So this is here line here, and you have to go here. If you create thin wall section, then you go only to this point and it will be automatically connected. That's the difference. Okay, it was a little bit longer than I expected, but I hope I have explained everything. Thank you very much.